Okay, so this is probably the hardest section of the year. So just kind of take a pill and we'll get through it. Um, so I wouldn't write all these words down. Um, with this, understand the problem, just read through it and try and figure out what's going on. Um, I'm going to highlight this, draw pictures, label, and using one variable, write an equation. So number two, I'd actually break into two parts. So after one, I go two, draw a picture. Number three, write an equation in one variable. Um, Sometimes we graph it, sometimes we don't, but we need to find the critical points and the endpoints. So we need to find the derivative, set it equal to 0, see where it doesn't exist, and figure out the domain. Then we're going to solve. Um, so basically, we're going to be um, finding out, is it a max or a min, by using our sign charts, and then interpret the solution and write a sentence to make sure you're actually answering the question. Okay, number one, find two numbers whose sum is 20 and whose product is large as possible. So every single question is going to somehow indicate a maximum or a minimum. Large just means we have to show our answer is a maximum. If we have two numbers whose sum is 20, does it make sense? Our numbers are going to be between 0 and 20. Okay, let's X be our first number. So then no matter what our first number is, whatever 20 minus that number, that would be our second number. And whatever we're trying to maximize or minimize is the equation we need to use to take the derivative of. Since we're maximizing our product, we need to find the product of these two numbers. Then we need to take the derivative, and we're just looking for our max and min stuff. And we set our derivative equal to 0, solve for x, and then we're going to insert our number into our endpoints. So we have 0, 10, and 20. So we're going to look at our derivative, and if I plug in 1, I get 20 minus 2, which is a positive. Plug in 11, 20 minus 22 is negative. So that means P is increasing, then decreasing, which is why this is proof this is a maximum. All right, now we always need to check our endpoints. So a lot of times what we'll do is just plug all this stuff in, make a table, and if x is 0, then our product is 0. If x is 10, we have 10 times 10, which is 100. Plug in 20, that's 20 times 0, that's also 0. So notice our endpoints here, these are minimums. And the question said, find two numbers whose sum is 20 and if the product is large as possible. So we're looking for the two numbers. So the two numbers are, in this case, they're the same, 10 and 10. Maximize the product. Okay. Example number 2. All right, we are going to inscribe a rectangle under one arch of the sine curve. So I'm going to draw it like this. So what is this end point here? We're going to start at 0. How far does it go up? We're going to go from 0 to pi. And I'm going to create a rectangle. I don't know if that's my rectangle. If that's my rectangle, the rectangle just has to fit in the sine curve. All right, so does it make sense where this hits the curve? I'm going over x, up, sine of x. That's the y value. That would be that coordinate point. So does it make sense that this height is going to be the y value? Our height of this rectangle is sine of x. Okay. So if this part is x here, does it make sense that this would be x? That length from here to here is x. So this length from here to here is also going to be x. So if the whole length across is pi, this length of my rectangle is pi minus 2x. So the height is where this hits the curve. That's why I'm using my y value of the sine curve. So my area is my length times my width, which equals all that. Now, because this is going to be not something we can do by hand, I want you to go ahead and take your graphing calculator. We're going to enter this into Y1. It's probably a good idea because once we get to the AP test, you can actually label certain functions, which one's Y1, which one's Y2. So go ahead and mark that as Y1 and put that into your calculator. I should probably do that too. Make sure your mode is in radians. It should always be in radians. Be really careful that you end. We'll always put in a parenthesis here. End this parenthesis. Use the pi key, which is the second up arrow. All right, and this is our window. This is our domain. So let's change our window to go from 0 to pi. And we can keep the -10 to 10. Oops, I did something goofy on my window. Oh, yeah, I put +10 for my, okay. So we want to find our maximum value. So we're going to go second, trace, go to max, and get your little cursor over there. Notice how there's just one max. So we're looking for this point right here. Oh. And I put +. plus. Hang on. This is not the graph. I put x plus 2x, or pi plus 2x, sorry. So this is the point we're looking for. You probably had this all right. But some dumb little things on the calculator. Hey, there we go. Okay, so the max occurs when x is 7.1046. And that's when the area, the y value, is 1.1221. Okay, so this is my x and this is my y. So you got to be careful here. We want to find, and what we also have to talk about is it's increasing and decreasing. So you can use your they call it your GDC, graphing display calculator, and show that this is a max. So kind of I'd sketch this all out showing what you did. So we have the largest area of, and here's our area, 1.1221. And this is, it doesn't have units, so we'll just say units squared. When, okay, so be careful here. X is not my dimension. The dimension is sine of x is our y value, and pi minus 2x is our length. So when the length is, so I'm going to take pi minus 2 times my x value. All right, so let's go second quit. Pi minus 2 times, plug in the x, 1.7206. Remember, you can just chunk it off after 4 decimals. And when the width is sine of this value, so plug that in, and that should give us 1.7. Oh, no. Oh, I look in the right spot. 0.6521. So you have to make sure we want the largest area and the dimensions that it gets. So sometimes your graphing calculator questions are worse because they're going to make you do a whole bunch of stuff on the calculator. So we can look at the graph and use the graph to be our justification, but you have to spell it all out. All right, here's our box problem. So how do we find the dimension or the volume? Let's read the question. An open top box is to be made by cutting congruent squares out of a corner. So it's 25 by 20, but we're going to cut out corners of x and fold this corner up. All right. And we want the maximum volume. So volume of a prism, length times width times height. If I fold this corner up, this is going to be x. If this starts out being 25 and I fold this x up and this x up, I get 25 minus 2x. And this will be 20 minus 2x. So length, width, height. So my volume, I'm just going to put the x on the outside because I like that better. Now we want to simplify. So let's distribute all of this. And I'm going to kind of go backwards because I want my x squared to be first. Then distribute the x. All right, now we're ready to take our derivative. And from the looks of my notes, this is not factorable. So when we set this equal to 0, we have to sing la 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 la. X equals opposite of b plus or minus square root of b squared minus 4ac all over 2a. That's pretty awful. All right, so if we plug all this into our calculator, we get two answers. When I add the top and divide by 24, I'm going to get, okay, one of my answers is going to be 3.681. My other answer is 11.317. All right, we didn't talk about domain, and usually when I get to this point, I'm like, oh shoot, we got to go back and talk about domain. So, if we think about this box, if it's a real world problem, it's always got to be more than 0, because it doesn't make sense if x can't be negative. So it's got to be more than 0. Now, what value would make this 0 is 12.5. What would make this 0 would be 10. So all of our answers have to be between 0 and 10. Otherwise, one of these lengths would be negative. X has got to be between 0 and 10, which means this one is not an option. Okay, so then we're going to look at, actually, let's use the second derivative test. So let's do the second derivative of this. So then it kind of gives us practice. 24x minus 180. And if we plug this in, the 3.681 in here, that gives us a negative value. So that means this is concave down, which proves, you have to prove that it's a maximum, either with sign charts. I mean, we could have also done 0 to 10, and then the 3.681, we would have found this to be increasing, this to be decreasing. This is one option. This is the second option. Either way, we have to prove it's a maximum, either using the second derivative test or our sign diagrams. All right, so we do have a maximum. What's the question? It said, how large should the squares be to hold as much as possible? So x, which is what we're trying to find, we need to cut out our squares where x is a length of 3.681 inches. That's what this mark is here. And if we plug this value in for our volume formula, the volume, if we use our calculators, plug it all in, has a max volume of 825.28 square inches. So you can write inches squared, cubed, sorry. Volume is cubed, cubic inches. So this is our final answer, but you get points for finding the equation, for taking the derivative, setting the derivative equal to 0, finding the points that maximize or minimize. You've got to prove it using the second derivative test or sign diagrams, and then you have to answer the question. All right, I think I'm only going to have time for one more, and then I'll do the rest of it on a separate video. Okay, so you have been asked to design a 1-liter oil can shaped like a right circular cylinder What dimensions will use the least material? Okay, so the first thing we have to know is quantity, 1 liter. This is quantity, this is volume. I've never seen that actually on the AP test where you have to know that. They will actually give you that information, but 1 liter is actually 1,000 cubic centimeters. How do we find the volume of a right cylinder? That's pi r squared h. And sometimes they even give you that. All right, so we know that our volume is this. All right, so we want to create the dimensions with the least amount of material. Is the material calculated by the volume? No. We're going to put this little equation on hold for just a minute. To find the amount of area that creates the material itself used, we have to look at surface area. So we have 2 circles, top and bottom. So that's pi r squared is the bottom circle. We have 2 of them. 2 pi r squareds, top circle, bottom circle, plus 2 pi r h. When we get a chance, when we're back in class, I'll give you a visual of this. It'll make it so much easier. But remember when I said we have to write an equation in 1 variable? Right now we have 2. This is where this equation up here comes into play. We have to solve this equation for h. So I'm going to divide both sides by pi r squared. And I get 1,000 divided by pi r squared. And I can replace this h with this because in this particular problem, we have been told we're dealing with a 1-liter bottle. All right. So our first step is substituting this. Now the kind of nice thing is pi's cancel. This r cancels one of these r's. I'm just going to rewrite this. And I'm going to move, this will be 2 times 1,000. And I'm going to move the r to the top to get us ready for the derivative. Now we want to, least means minimum. We want to minimize our surface area. So we take the derivative of the surface area, use the power rule. 2 times 2 pi is 4 pi r. Negative 1 times 2,000 minus 2,000 r to the negative 2. I'm just going to go ahead and put that negative 2 down to the bottom. Now I'm going to set it equal to 0. And what we're going to do, I'm actually going to add this over. This is going to make this problem easier. Like this. And I'm going to multiply by r squared and make that r to the third. And I'm going to divide by 4 pi. So I get r to be the cube root of 500 over pi. So that's my radius value. That kind of sucks. Oh, and then my notes just quit on me, so hang on. All right, so what dimensions will use the least amount of material? So I wonder if they used a graphing. Hang on. Yeah, they used a graph. The other thing you could do is we can do the second derivative, and our second derivative is going to be 4 pi And then if we move this back up, -2, that'll be plus 4,000 over r to the third. This is always going to be positive because r is always positive. And since the second derivative is greater than 0, that means it's concave up, which means our prime point of r equaling this is going to always be positive. So this is going to be a minimum. So the dimensions themselves, this is our radius. And if we plug the radius back in up here, we get the height to be something. Oh. All right, I'm going to jump to the easy answer. 2 cube roots of 500 over pi. All right, so this is pretty awful. We'll actually work through some problems and it will get a little better. It's not quite this terrible.